The Moon, our only satellite. Barren and void of oxygen and life. Where temperatures on its surface range from a blistering 230 degrees Fahrenheit to a frozen minus 290 degrees at night. Here, there is no weather, no wind. It is serene, still, unchanged for millions of years. Beyond it, the Earth. Surrounded by a thin gaseous layer, its surface often remains hidden beneath the ever-changing veil of clouds. This layer of gases protects the Earth from harmful solar radiation, limits the temperature extremes, and contains the weather that scars and molds the features of its surface. On Earth, there is never such a thing as no weather, and the rate at which our atmospheric conditions change can be dramatic. As pilots, we must become attuned to the atmosphere and the weather it contains. Since the air is our medium of movement, understanding weather phenomena and the forces behind them are important considerations. The atmosphere that surrounds the Earth is relatively thin. Although it extends several 100,000 feet into space, about half of the total atmosphere is compressed below 3.5 miles. Many people have the false impression that the atmosphere is mostly comprised of oxygen, but in reality, only 21% of the total gas is oxygen. Nitrogen makes up most of our atmosphere, with carbon dioxide, argon, and other gases making up the remaining 1%. The atmosphere is made up of several basic layers, with the lowest layer being the troposphere. This layer slopes upward from about 20,000 feet at the poles to about 60,000 feet at the equator. Most of the weather which you will be concerned with will be found within this layer. Above the troposphere is a thin layer known as the tropopause, which acts as a lid on the troposphere, keeping most of the moisture within the layer below. The stratosphere extends to about 22 miles above the surface. The air within this layer is very dry and stable. Few cloud formations penetrate into this layer. Above the stratosphere are the mesosphere and the thermosphere. These layers have very little effect on the weather. The gases in the atmosphere contain molecules that are constantly in motion. As the air is heated, these molecules speed up, creating more space between them. The result is fewer molecules per given volume of air. When the air is cooled, the molecules become less active, meaning more can exist in a given volume of air. This cooler air is heavier and denser than the warmer air. The differences in air density are the basis for the movement and circulation of the atmosphere. To demonstrate this principle, suppose we have two rooms, one which contains cold, dense air, while the other has warmer, lighter air. When the door is opened, the air begins to mix. The heavier, colder air slides under the warmer air, creating a cold draft on the floor. As the cold air fills the bottom of the room, the warmer air replaces the colder air. On a larger scale, the draft created between the rooms is called wind. Air replacement due to these density changes drives our major weather systems. This density difference is due to the pattern of global heating. At the equator, light from the sun strikes the surface at an almost perpendicular angle. Near the poles, the surface of the Earth is largely turned sideways to the sun. This results in more atmosphere between the sun and the Earth at the poles. This greater amount of atmosphere cuts down the intensity of the sun's rays. Also, the same amount of light that would cover a given area on the equator is distributed over a far larger area at the poles. The result is less heating energy per square mile. As the sun's radiation heats the tropical areas of the Earth, the air becomes less dense and rises. Because less dense air does not exert as much pressure, a permanent low-pressure area forms near the equator. Nearing the top of the troposphere, the warm air is displaced sideways, away from the equator. The air continues northward and southward, slowly becoming cooler until it begins to descend near the poles. This colder descending air creates a permanent high-pressure area near the poles. The air then returns along the surface, back toward the equatorial areas to replace the rising air. If the Earth didn't rotate, there would be a continuous circulation pattern from the polar highs to the equatorial low. But because it does, this theoretical one-cell circulation pattern becomes a three-cell pattern. In this circulation pattern, the air near the equator still rises and flows toward the pole. But this branch, known as the Hadley cell, only reaches about 30 degrees north. Here it combines with sinking air from the Ferrel cell that corresponds with a semi-permanent subtropical high-pressure area. Near 60 degrees north, the warm surface winds of the Ferrel cell and the cold winds of the polar cell collide, rising to produce an area of low pressure. In addition, these airflow patterns are affected by Coriolis force. In order to better explain how Coriolis works, let's use the example of two ball players attempting to play catch on a merry-go-round. As the pitcher throws the ball, it travels in a straight line, but not to the catcher. To the thrower's perspective, some force seems to be turning the ball to the right. This same situation applies to air as it flows from the North Pole to the equator. Because of the Earth's rotation, the wind seems to be deflected to the right. This apparent rotation is called Coriolis force. Atmospheric pressure, or the concentration of air molecules over a given area, is measured in terms of inches of mercury, or millibars. 1 inch of mercury is equivalent to approximately 34 millibars. The measurement of pressure is done with the use of a barometer. This instrument is nothing more than a partial vacuum within a glass tube containing mercury. As the pressure of the air exerts a force on the container of mercury, the mercury will rise. The average atmospheric pressure of the Earth will make the mercury rise 1,013.2 millibars, or 29.92 inches. This measurement is considered to be standard pressure. During periods of higher atmospheric pressure, the force exerted upon the mercury is greater, which forces the mercury to rise. The reverse happens during periods of lower than standard pressure. If we imagine standard air pressure as a plane, we can visualize the relationship between air masses with different densities. On the left is a high-pressure system, or a mass of denser than standard air. It is more dense at the center of the mass. On the right is a low-pressure system, or a mass of less dense air. Pressure changes occur more rapidly directly between the center of the high and the center of the low. As we rotate the image to a top view, we can draw lines around the areas that appear to have the same height, or in this case, the same amount of atmospheric pressure. These lines are called isobars, and they are drawn on weather maps to represent areas of equal pressure. By using these lines, you can determine the position of high and low pressure areas. You can also tell how large or severe they are by the number of lines and how they are placed. Notice how the isobars are closest together directly between the high and the low. The closer the lines, the stronger the pressure gradient. Air from a high-pressure area will flow directly toward a low with a force which relates to the pressure gradient. If the Earth didn't rotate, highs and lows would exchange wind directly in this manner. However, Coriolis force from the rotation of the Earth is also acting on these systems. As winds spill off a high-pressure area in the northern hemisphere, they are deflected to the right. This results in a clockwise flow around a high and a counterclockwise flow around a low. As the wind is driven around these systems, the air closest to the surface is slowed by the friction of the ground. When this happens, the Coriolis force is diminished until the pressure gradient force becomes greater. The resulting wind tends to flow across the isobars toward areas of lower pressure. At altitude where airflow is not affected by the surface friction, the wind continues to flow parallel to the isobars. In addition to creating large patterns of wind around highs and lows, differences in atmospheric density can cause wind flow on a local level as well. In areas near the ocean or other large bodies of water, local changes in heating and atmospheric density can cause daily wind flow patterns. During the day, water slowly absorbs heat. On the nearby land, the sun's radiation only penetrates a few inches into the soil. The land surface heats up much quicker than the water. As the air over the land warms up and begins to rise, air over the water is being cooled down because of the cooler surface of the ocean. The cool air then flows inland to replace the rising warm air. This produces a sea breeze flowing inland from the ocean. During the night, the land cools very quickly. The air above the landmass begins to cool and sink. The ocean, now warmer than the land, begins to warm the air above it, causing the air to rise. The flow of the cycle now reverses, and in the evening, a land breeze will be experienced. Local wind patterns can also form as the result of mountainous terrain. One of these is a foehn wind, which occurs when there is a mass of cold, dense air near the top of a mountain range. As the air pushes over the top of the range, the cold air begins to descend down the other side. As this air accelerates and replaces the warmer air beneath it, it begins to compress and warm up. As the air heats, it will eventually become warmer than the air it is replacing. This causes the atmosphere at the bottom of the hill to become warmer. These winds can become very strong, with gusts exceeding 120 miles per hour. In the Rocky Mountains, they are called Chinooks. In the Sierra Nevada mountains, they are the Santa Ana winds. Regardless of their names, these winds can produce large amounts of damage and are hazardous to aircraft, both in the air and on the ground. They can occur during what would normally be perfectly good VFR weather, and is one of the reasons surface wind reports are important to you when receiving a weather briefing. We have seen how heating and the differences in air density can produce wind. The other major force in the formation of weather is moisture. Moisture occurs on our planet as a solid, a liquid, and a gas. Within these states, it can take many forms. We see moisture as clouds, as rain, hail, or as snow, ice, or water. Dew and frost are also forms of moisture. How water changes back and forth from state to state is very important to the formation of weather. We have all experienced the effects of evaporation, such as water evaporating from a lake. When water turns from a liquid to a vapor, the process requires heat. This heat energy is drawn from any available nearby source and is stored by the vapor. When the water vapor is returned to a liquid through the process of condensation, the latent heat that was stored during evaporation is now released. The heat exchange during evaporation and condensation is a major factor in the vertical movement of air columns. Thunderstorms, for example, can be developed by this force. Originally, the air begins to rise through a force such as the sun heating the surface, which in turn warms the air above it. As this warm air cools and eventually condenses, the latent heat released from condensation will, under the right conditions, continue or increase the strength of the updraft. If this process continues, a thunderstorm can develop. In vapor form, molecules of water exist between other molecules contained in the atmosphere. When the air is warm, more room exists between the molecules of air. Therefore, more water molecules can squeeze between the air molecules. When the air is colder and the air molecules are closer together, less water vapor can fit between the already close air molecules. For this reason, cold air cannot hold as much water as warmer air. Dew point is the temperature at which an air mass becomes completely saturated with water vapor. In other words, it will hold as much water as the temperature will allow. When an air mass becomes completely saturated, condensation occurs. Let's say that we have an air mass with a temperature of 55 degrees Fahrenheit. If the dew point is also 55 degrees, then the air is 100% saturated. If condensation nuclei are present, then condensation will occur. Clouds, fog, and dew are all forms of condensation. When water that is formed on the condensation nuclei becomes too heavy for the atmosphere to support, then precipitation occurs. Since the moisture content in an air mass is relatively constant, the air mass must usually undergo some form of cooling in order for condensation to occur. For example, if the air is 50% saturated at 55 degrees, then the air must be cooled to about 37 degrees in order for condensation to occur. When the temperature reaches 37 degrees, this air mass will be 100% saturated. Weather is something that we must deal with daily as pilots. It is constantly changing and infinitely complex. Knowing the basic driving and manipulating forces of our Earth's weather patterns will help you to understand the more detailed conditions and concepts that will be introduced in the following weather sections. Being able to understand the concepts of weather development will not only help you understand the current conditions, but will also help you anticipate future changes as well.